My name is Stefan Dörr, CEO of NODE Robotics and one of the co-founders. And I would like to talk about highly flexible intralogistics through collaborative AMR fleets, which is what we are working on currently. I hope my internet connection is sufficiently stable. I experienced some problems during the day. If there are problems, please let me know, then maybe I will shut down my camera or try something like that.
I will do.
Great. So let's start. I have a short outline here for you. So first of all, since we are like a fresh startup, I would like to give a quick overview about NODE Robotics, and then I would like to dive into the field of robotic fleets, mobile robotic fleets, and what autonomy is doing there and is helping to bring those robots on the shop floors. And then I would like to present our NodeOS, the product that we are working on, and then conclude with a short summary. So NODE Robotics was founded in 2020, last year. We are a startup from Fraunhofer IPA, which is also hosting this amazing conference here. We are strongly growing. Current team size is 9 full-time employees and 20 part-time employees / students located in Stuttgart. Actually, we are part of the Arena 2036, which is a research campus from the University of Stuttgart. And yeah, if you're like in Stuttgart and have time, feel free to get in touch to visit us there. We have a nice demonstrator, which I will also show some videos from later on. But happy to welcome you in this nice location. So we already have gained some traction in industry, which is also due to our Fraunhofer background, where the core team already worked together for more than 5 years on the technology. So key figures here, as of by now, we have more than 450 AMRs running with our software in productive usage in industry, having driven more than 125,000 kilometers so far. And we have already enabled 27 different AMR types, which should prove that like hardware and sensors agnostic software development is basically our thing here. We have two lighthouse projects that I would like to briefly outline here. First one is already like a few years ago and is more kind of node history, because it's basically where we started and where we're coming from. Was a project with Bear Automation, which is a local HEV supplier at a Audi sports car manufacturing plant, and where we provided our navigation software for this HEV that you see in the picture, and which is like used for carrying the car bodies through the manufacturing process. And as far as I know, this happened in 2015. This was one of the first application of ROS and SLAM in this kind of critical part of the manufacturing process. We were quite happy to successfully finalize this project, but we also like experienced some drawbacks, some limitations, and of the current solution, and also like saw the potential of doing better, and that's what we basically did. Went back into more research phase and then completely rewrote our software stack and came up with the next generation of it, which is running currently in our biggest project with BMW, where we provide our navigation stack for the so-called smart transport robot that you can see here on the right picture. Current status here, we have 400 of these AMRs running in 7 production plants worldwide. in productive usage. And we are particularly proud of this one because here we really showed that our software is able to handle all these different environment applications, highly dynamic, large-scale environments, and with one single software. All right, that's my quick overview of our Node, and then I would like to motivate our topic here and step into the status quo of flexible intralogistics, the way we see it. I guess it's common sense that HEVs, AMRs have the great potential to become the de facto standard solution for flexible intralogistics, but are still a niche. I think numbers from 2019 from the World Robotics Report, we had 70,000 units, HEVs and AMRs included, whereas we had I guess 2 million forklift trucks. So there's still a steep road ahead. The major reasons why HEVs, AMRs are not yet not yet the standard solution, the way we see it, are the followings: that current solutions at least lack one of the following points here. First is some of them still have pretty high initial investment and integration costs, which is particularly harmful in the SME sector in trying to adapt the technology. If a fleet is set up once, it's usually really hard to expand it or scale it or basically adapt it. Also, if there are changes in the environment, that's usually pretty hard. Then we have the typical issue of green versus brownfield. So most of the installations happen in greenfield, whereas it's hard to get those systems running in a brownfield application. And then there is the big issue of interoperability. So the lacking capability of operating multi-vendor fleets. To overcome these issues and enable the widespread usage, we see that a solution has to fulfill the two main key components, that is multi-vendor and plug and play. And the two key ingredient, the way we see to achieve this, is first of all standardization. I guess that's not really controversial here. If you want to have a interoperable solution here, if you want to operate multi-vendors, and if you want to easily integrate HEVs, AMRs, then standardization is one key ingredient. And the second one is autonomy skills. And this one might be rather controversial. That's why I would like to spend 2 slides on motivating why we need autonomy here. First of all, what do we mean with autonomy within this context? So not on a philosophical context, but on a technical one. And first of all, I have a definition from the National Norm Institute from the US, from the NIST, which says a robot is defined as autonomous if it's able to accomplish its assigned mission within the defined scope without human intervention while adapting to operational and environmental conditions. I really like that definition, but still it somehow indicates that this autonomy is a binary state. Same holds for the usage of the words HEV and AMRs, which also indicate there's kind of like the HEVs on the one side and the AMRs on the other side. What we propose is instead that this is rather a continuous state, and we suggest to use a level of autonomy instead of this binary usage. And I've plotted here some features or capabilities which I think pay in for increasing the level of autonomy. So typically, if you have a physical line guidance, then your level of autonomy is pretty low, and you can increase it by virtual line guidance, by dynamic path planning. Also, if you have like a SLAM-based localization, which doesn't use markers. I don't want to get into all these deeply, but like overall, we see that once the robot is more and more able to adjust to the environment, to integrate into the environment, and also to adapt to changes of the environment, then it's the autonomy level increases, and then there is also like the reason why a plug and play is only enabled via autonomy. So far, we just talked about single robot, but now how do we bring this autonomy to heterogeneous fleets? And I've the two major control architectures here, which I want to shortly describe with all their advantages and disadvantages. First of all, central control architecture, typical master-slave approaches, which is as of by now the most dominant approach, like having this central fleet control, master control, which controls all robots or HEVs, and the HEVs themselves stay pretty pretty limited in their what they can decide, and basically everything's happening on the master control side. The advantages are low complexity, high transparency and determinism, and also that with this approach we can exploit server resources for making or for executing decision-making algorithms. On the downside, we obviously have a single point of failure. We have the control latencies via communicating these decisions from master to slave, and we're doing that, or we are making our decisions without actually the knowledge of the robots, what they are seeing locally. On the other side, we have decentralized approaches, also typically called swarm intelligence, which isn't quite correct, but I would still use it here, where the approach is to make decisions locally, to have intelligent agents which strongly collaborate. And obviously the upside here is you get rid of the server connection on the dependency. You more and more come to a actual real-time perception and control architecture. Or on the downside, there is data and state synchronization, which you need to do continuously, and also increased local hardware demands. So the good thing here is it's also not like a either-or decision, but you can basically combine those two, and that's what we propose here, to go with a hybrid approach to exploit the advantages and strengths of the both approaches here. And that's what we are basically following on with what we call the NodeOS as the base architecture. What is NodeOS? NodeOS is a end-to-end software solution based on ROS for the particular use case of coordinating, orchestrating, and controlling heterogeneous AMR fleets in industrial applications. End-to-end in a manner that it's really acting from the cloud to the edge. So from like receiving and allocating transport jobs up to actually navigating and steering the robots. And we build it highly modular in a way that we can easily configure it for the diverse applications we see. It basically consists of 4 modules, which I want to shortly describe here. I will have more deeper descriptions later on, but just to give you an overview, we have the NodeEdge module 1, which is deployed on the robots, and which basically serves for advanced autonomous navigation. So basically, brings the intelligence to the robots. And then we have module 2 and module 3, which is our approach to a fleet management of AMRs, which is like containing these decentralized and centralized approaches here in one architecture. So the NodeMesh is actually the decentralized part of it, where we enable decentralized data sharing and direct collaboration between the robots. And then we have the Node Services, which is a cloud-based services for the overall topic of fleet management and coordination. We also have module 4 here, node support, but yeah, it's just that our module for technical support, and I would go deeper into that for now. The whole system is based on ROS. We are a strong ROS supporter, and we see that like open source and community-driven development is the way to build modern software. We also have a decent open source strategy in a way that we also open source many of our packages. So I would like to go a bit deeper into those modules and also show you some videos. I hope that the internet connection is good enough to stream the videos. First of all, the NodeEdge. As already mentioned, this is the software component that we place on the robots. And key characteristics here, it's highly hardware and sensor independent, so we can basically use the typical sensors, typical hardware setups without any infrastructure installations needed. So we have a strong focus here on being robust to environmental changes to operate in highly dynamic scenes. Core components is LiveSlam, dynamic path planning, dynamic route planning, and I would directly go to a short video I have for you, which is actually our screencast from one of our robots in productive usage that you can see here. And it shall demonstrate that we are really able, without any markers, without any installations, to operate in this really highly dynamic and large scale environment. One focus for getting those robots running here was like the LiveSlam part. So we are continuously updating our map here, which is crucial because we have areas where we don't have any static structures at all. So you really need to take all the semi-static objects like the pallets, boxes, everything that you see with the 2D LiDAR into account. So there is no option to just like rely on static objects because they are not sufficiently there. And then the second focus here in this project is that we have like huge and varying safety fields due to that this robot is able to load up to 1 ton and is able to drive up to 2.5 millimeters per second, sorry. And if we, as you can see, since we're doing like collision avoidance and dynamic path planning, really need to take those huge safety fields into account and actually to optimize our local path based on this safety field configuration. Coming to the second module, so now we basically had like robots navigating autonomously, but they usually operate in a fleet, and with the NodeMesh we enable that those robots directly communicate and interact with each other. We're using like Wi-Fi for that for now, so it's not really a mesh architecture, but like it's the concept of a mesh architecture where there is no central instance but a direct communication among the robots. And one applications we have here is our collaborative motion planning. So our approach to our traffic management is to use the capabilities of those AMRs in terms of dynamic path planning and let them resolve conflicts locally and using their power and their capabilities, basically, instead of having a central instance which does the traffic management here, which opens up the possibility to let those robots seamlessly operate also in narrow environments and also in changing environments to actually optimize their path and routes based on real-time information. I also have a video here which demonstrates how it's working. We are basically doing a direct communication from the robots that are involved in the conflict. They are exchanging their trajectories and then mutually optimizing those trajectories. And you can see we're really having like here a heterogeneity in terms of what hardware or robots we are able to use for this. So it's really agnostic to kinematics and also to the sensors being used. So that we really open up a heterogeneous fleet control here. Right, I would step over here a bit, looking at the time. The last module I want to quickly demonstrate is our Node services, which was this cloud-based instance or cloud-based services for fleet management and coordination. We are having a multi-scale cloud service architecture here to actually have different services and for the overall topic of managing the fleet. And based on what's actually needed in the application, we can then just enable and disable the right ones. We are basing from an interface perspective on the first standard here, the VDA 5050, the first German standard here for communicating between AGVs, AMRs, and the fleet management system, but we extended this one with our open API in order to get more like the AMR's features and capabilities also in there. One component of Node services is the live map server. So the idea here is to collect the map data from the robots and fuse it into a consistent global map so that we centrally keep and update a global map, which then is used for routing of the fleet, so to route the robots based on the latest environment information on the latest map, but also for the robots themselves in order to stabilize their localization, which is based on the map. And the hard part here is that we are dealing with like heterogeneous sensor data. We have heterogeneous sensors mounted on different heights. So we need to fuse this all into a consistent global model so that we are really able to leverage the information and provide it to the robots. With that, I would like to summarize my presentation. We see a rising demand for multi-vendor and plug-and-play solution in order to enable widespread usage of AMRs. And we see standardization and autonomy skills as the key ingredients. I also talked about autonomy and why we think it's not binary, but rather a continuous state, and a high level of autonomy actually enables this plug-and-play usage. We also talked about control architectures and saw that neither purely centralized nor purely decentralized are doing the job if we really want to open up highly autonomous fleets, but rather hybrid controller architectures are the way to go here. And with our NodeOS, we are like working on a end-to-end solution which uses this kind of architecture and which is designed for operating multi-vendor fleets. Thanks for listening, and I'm glad to have your questions.